Okay, so the next thing we're going to learn about is how to write exponential forms of an expression in logarithmic form and how to do a logarithmic exponential form. So we're going to start off with this one. So log to the base 4 of 64. What number do we need to raise 4 to get 64? Well, 4 to the third power, 4 times 4 times 4 is 64. So log base 4 of 64 is 3. So the equivalent exponential relationship, which shows the same relationship between these numbers, is 4 to the third power equals 64. So to go from the logarithmic form to the exponential form, this is the base, this is the exponent, this is the answer. So log base 7 of 1/49th is -2. So the corresponding exponential expression, the base is 7. So we write that down just like 4 is the base. The exponent is the right-hand side, and this is the answer. So 7 to the -2 power is 1/49. So these are the equivalent logarithmic and exponential forms. Okay, so here we have log of 4 base 32 is 2/5. So this is your base, 32 raised to the 2/5 power equals 4. Now here we have something, natural log of 4 is 1.386. So the base is e, because it's the natural log. So you'd say e to the 1.386 power equals 4. So that's the logarithmic relationship. This is the exponential relationship. And the key thing is if you have, it's instead of being log to an integer base or just any base, if it's specifically to the base e, then you have to have e over here and natural log over there. And you can go the other direction. So here's an exponential expression which says 5 to the third power is 125. So your base is 5, so it's log base 5 of the right hand side, 125 equals the exponent. So let's try this. So this is the base, so it's log base 9 of 27 equals 3/2. And that's because, if you think about it here, the square root of 9 is 3. The square root is to the 1/2 power. And if you take 9 to the 1/2 power cubed, so if you cube this, 9 to the 1/2 power cubed, it's the same as 3 cubed, which is 27. So that's how the whole thing comes apart. Here we have 10 to the -3 power is 0.001, so the equivalent logarithmic expression would be, this is your base, log base 10 of 0.001 equals -3, and you can do the same thing here with this natural log. So you've got e, so that means the base is e, which is the natural log. You could think about that as log to the base e, so the base is e, but instead of writing log base e, we write natural logarithm. So log base e, you write the right hand side equals 3. So that's going the other way. And sometimes they ask you to evaluate logarithmic expressions without using the calculator. But even using the calculator, this is not easy. That's probably one reason they do it, instead of having to use your calculator and change base formulas. So the way you do this is you ask the question, what did I raise 16 to get 4? So what you can do is you can think about just trying some values here, see what you get. So 16 raised to the first power is 16. 16 raised to the 0 power is 1. So 4 is between 1 and 16, so it's somewhere between 0 and 1. So it's probably some kind of fraction. So it's between 0 and 1, so let's try the 1/2 power. So 16th of the 1/2 power is the same as the square root of 16. And the square root of 16 is 4, and that matches up. So that works out pretty good. So it's still the answer is 1/2. What else can we say here? Yeah, this just some problems showing using the inverse properties of logarithms and exponents. So if you've got some function g of x is the natural log of x, where x is equal to e cubed, then you can substitute that in here. And the natural log of e to the 3rd power, because the natural log and exponential are inverse functions of it, is f of g of x equals x, where in this case x is this exponent. So we're just using the inverse properties of logarithms. And you can do the same thing here. So if we've got some base b, and then you have b raised to the -3 power, log to the base b of b to the -3 power is just -3. Just checking to see what I got left here to show you in this section. Okay. Right now, I'm probably going to talk a little more about it. Okay, then they talk about finding the domain, x-intercept, and vertical asymptote of logarithmic functions. So here we have the g of x is log to the base 6 of x. So the only difference between this and what we saw earlier, we did log base 2. So it's just going to be a similar shape, just either flatter or vertical, depending upon what this is going to happen. So our domain is still from 0 to infinity. We still have a vertical asymptote at x equals 0, like we did for log to the base 2 of x. The x-intercept is always equal to 1. The x-intercept is when y equals 0. So you set this equal to 0, and you say, you know, what power do I need to raise 6 to get 0? And the answer is, yeah, that's not what I'm thinking. So when the base and x are the same value, no, again. So I guess the easiest way really is just to say the x-intercept is always going to be 0 when you just have a function where there's no transformations of any kind. All thing that's changed is the base. So the x-intercept is 1, and the vertical asymptote is still at x equals, is the vertical line, x equals 0, or the y-axis. So this is what it looks like. Pretty much looks like the one that we had for log to the base 2. Log to the base 2 still had a x-intercept of 1, but instead of when x equals 2, y equals 1, and when x equals 4, y was equal to 2, and when x was negative, when it's 1/2, this is -1. So what happens is the function kind of gets flattened out. So this is log base 2 of x, and this is log base 6 of x. So that's what happens when you have a higher base. It flattens it out like that. Now here we have a function that has some both horizontal and vertical shifts to it. So the previous function was just log to the base 6 of x. So we have a parent function, log to the base 5. And then we're going to shift it in the x direction. We're going to shift it in the y direction. So because of this shift here, the domain gets moved. And again, it gets moved depending upon what's going on here. We have x minus h. So h is equal to 1. So that means we're going to shift everything horizontally, including the vertical asymptote. And therefore, the horizontal shift also changes the domain. It also shifts that to the right 1 unit. And then here we have plus 4, so that's going to vertically shift everything as well. So let's see how that works. So let's add a page, get some graph paper. So what we're going to do is we're going to plot the parent function. And I'm going to make this go to 10, 10, negative 10, negative 10. Okay, so what we're going to do first is we're going to plot log base 5 of x. So this is a logarithmic function without any kinds of shifts. So these are the things that we could do. We could plot the x-intercept, which is 1. We know when x equals 5, 1, 2, 3, 4, 5, that we're going to have a value of 1. And so we're going to know that log to the base 5 of 5 equals 1. We also know the log base 5 of 1 equals 0. That's this point. And we also know that log base 5 of 1/5 equals negative 1. So if we go to 1/5, negative 1, it's going to be about right there. So you can kind of figure out what's going on like that. So that's what the base function looks like, or the parent function. Now, what's going to happen is we're going to shift that thing horizontally 1 unit and vertically 4 units. So I could grab that and shift it, but what we want to do is we want to draw a new vertical asymptote, and we're also going to draw a new axis 1, 2, 3, 4. So what I've done is I've kind of shifted the origin 1 unit in the x direction, 4 units in the y direction. And then relative to that new transformed axis, I can put this point in, which is 1 unit to the right of the original axis. So I put that there. Then you had this point, which was 5 units, 1, 2, 3, 4, 5 units, because it's base 5. So you go 1, 2, 3, 4, 5, up 1. So there's that point, shifted. And then we got this point, which is 1/5 of a unit and down 1. So with that, I can now kind of sketch in the transformed function. Now, I really don't, these two things were just to guide me. So this is my transform function with the original coordinate axis, but it does have vertical asymptote here at positive 1. Instead of going through 0, 1, it goes through 2, 4. So this black function here was y equals log base 5 of x, and this transform function is log base 5x minus 1 plus 4. And you can see here, better sketch, but you can see how I've got the green shifted over 1, up 4, based on the transformations. This point is 1 unit from the shifted origin. This is 1/5, negative 1. This is 5, 1. And there is your homework assignment.